Imagine you have this incredibly brilliant employee,
Right.
and you want them to make you a cup of coffee.
Okay, a pretty standard request.
Yeah,
Yeah.
exactly. But instead of them just intuitively knowing how to do it, you hand them a 10-page, highly detailed instruction manual. You spell out literally everything, like locate the mug, ensure the mug is clean, grind the beans to this exact coarseness.
That sounds exhausting.
It is, and they read the entire thing, and I mean, they make the coffee perfectly. But then an hour later, you want another cup of coffee, and you have to hand them that exact same 10-page manual all over again.
And they have to read it all again.
Right. Sure, you get your coffee, but the agonizing inefficiency of that interaction, well, that is exactly how we are currently treating AI agents.
It is a massive technical tax. Because right now, as large language models are deployed as agents, to browse the web, execute code, or parse complex data, we are relying on what we call hard skills.
Which are basically just giant text files, right?
Exactly. We give them these massive markdown files filled with instructions, answer policies, and procedures, and we feed them that exact same text file every single time we run an inference.
Which brings us to the focus of today's deep dive. Welcome, by the way. Today we are looking at a state-of-the-art research paper titled SoftSkill, Behavioral Compression for Contextual Adaptation.
It's a fascinating piece of research.
It really is. The researchers here are proposing a radical shift. They're asking, what if we don't force the AI to read the manual every single time? Like, what if we could take that massive markdown document and compress the underlying behavior into a tiny piece of, I guess you could call it mathematical muscle memory.
That's a great way to put it. Muscle memory that just lives permanently inside the AI's context.
Exactly. So setting the stakes here, what are we really looking at with this behavioral compression?
Well, they are targeting the process of taking hundreds or even thousands of readable human words and shrinking them down into just a few dozen mathematical virtual tokens.
Wow, just a few dozen.
Yeah. The goal is to create a latent behavioral prior. It guides a completely frozen base model, essentially giving it the instinct to perform a specific task without ever having to actually parse the English instructions.
To really grasp why this is so necessary, we should probably look at the fundamental flaw in how we use hard tech skills today. I mean, deploying a natural language markdown file for, say, an earnings report extraction task is great for us.
Right, because humans can read it.
Yeah, we can read it, debug it, version control it, but for the model, English text is really just a proxy for the behavior we actually want.
Precisely. Text is not the behavior itself. During a forward pass, the model has to translate that long text artifact into hidden state dynamics that actually shape the token generation.
It has to do all that translation on the fly.
Every single time. It has to map your English instructions against its own internal latent space, figure out which attention heads need to activate for the specific policy, and then try to execute it. And like you said, it rebuilds that state from scratch for every generation.
Which just eats up your context budget.
It consumes massive amounts of budget, and frankly, it creates a serious alignment mismatch.
Right, because what makes sense in human syntax doesn't necessarily map cleanly to the model's internal geometry.
Exactly. You might write an instruction that is perfectly logical in English, but it happens to conflict with the internal control directions the model learned during its pre-training or RLHF phases.
Oh, I see.
Yeah, a verbose natural language skill that works beautifully for one specific model architecture might just completely confuse another. It leads to hallucinations or ignored constraints.
So if forcing the model to constantly translate English instructions into internal logic is the bottleneck, the researchers basically needed a way to bypass the translation entirely. They want to give the model the instinct directly.
Exactly.
Okay, let's unpack this. Structurally, how are they actually achieving this compression? I mean, if they aren't just putting the text in the prompt and they aren't doing a full model weight update like Laura, where exactly do these virtual tokens live?
It is a very elegant approach. SoftSkill takes the original natural language text skill and uses it to initialize a compact soft prefix.
A soft prefix.
Right. Think of this as a continuous vector representing a small string of, let's say, 32 virtual tokens. Now, the base model...
Which in this study were the Quen models, right?
Correct. They used open-weight Quen models like Quen 3.54b. That base model remains entirely frozen. You are not updating billions of parameters. Instead, you only train a soft delta.
The soft delta being the mathematical difference applied to that initial 32 token prefix.
You got it. They train just this tiny delta using next token prediction on successful task trajectories.
So they just show it examples of the task being done right.
Exactly. They feed the model examples of the task being executed correctly, and they backpropagate the loss to optimize just those 32 virtual tokens to predict the correct sequence.
Okay, so it's fundamentally different from a reward model that just scores candidate answers at the end of the process.
Yes, very different.
And because the base model is frozen, you aren't risking catastrophic forgetting where the model just, loses its general capabilities to learn one specific skill.
Exactly. You are optimizing a tiny, continuous contextual control vector. By injecting this mathematical object into the context window right at the start, you precondition the model before any actual task tokens are sampled.
Oh.
It biases the frozen model toward the exact behaviors that were useful during the supervised training.
It almost feels like a chef's mise en place,
I like that comparison.
Right. Instead of the chef having to read the recipe, walk to the pantry, find the onions, chop them, and arrange them while trying to cook, the 32 virtual tokens prearrange the mental workspace. The attention heads are instantly biased toward the right ingredients and the right steps before the actual processing even begins.
That is a highly accurate way to visualize it.
Yeah.
You bypass the need to read the recipe. You are preloading the working memory with the optimal conditions for success.
Which sounds incredibly efficient in theory. But we really need to look at the benchmark data because, a theoretical mise en place doesn't mean much if the model actually fails to cook the meal.
Fair point.
They tested this method on single-round question-answering tasks, specifically Search QA for retrieval, Live Math for reasoning, and Doc VQA for visual document parsing. And the compression ratios they achieved are just phenomenal.
The efficiency gains on the input side are staggering. Take Search QA, for instance. The baseline used a hard text skill, a markdown file, that was 2035 tokens long.
Over 2,000 tokens just for the instructions.
Right. Using SoftSkill, they replaced that massive document with just 32 virtual tokens.
Unbelievable.
And the accuracy didn't just hold steady, it actually improved from 72.0 to 76.4.
That is a 63 times reduction in instruction length, yielding a higher accuracy score. And the live math benchmark was even more extreme, wasn't it?
It was. They took a 671 token text skill, compressed it into 32 virtual tokens, and the accuracy leaped from 37.1 to 60.5.
Which is a massive performance jump for math problem solving. I mean, that's a domain where models typically need expensive contextual prompting just to maintain logical consistency.
Exactly. And they achieved that while completely removing the human-readable instructions from the context window.
Okay, now I have to challenge something here, because it wasn't just the input context that shrank. The paper shows the average generative output tokens absolutely plummeted.
He did.
Like, on live math, the average output dropped from over 4,400 tokens down to just 6 tokens.
Down to 6.
When I see an output drop from 4,400 tokens to 6, my immediate suspicion is that the AI isn't actually reasoning more efficiently in its hidden states. Is this just an artifact of the training data? Like, did it just learn to spit out the final answer because the successful trajectories they trained the prefix on lacked chain of thought reasoning?
What's fascinating here is that you've hit on the exact mechanism at play. It's a critical distinction to make. The output reduction is absolutely a consequence of the supervision format.
Ah, I knew it.
Yeah. The next token prediction targets in their data set were direct answers. There were no intermediate scratch pads, no long chain of thought rationales. The prefix was simply optimized to induce highly concise responses.
So we shouldn't look at this and think, wow, SoftSkill found a way to mathematically compress complex multi-step reasoning into a 6-token output.
No.
It just learned a formatting preference for brevity based on the loss function.
Exactly. The researchers are very transparent about this. The reduction in generated tokens is highly advantageous for deployment. I mean, it saves massive amounts of compute and time, but it's not proof the model discovered some hidden compressed reasoning procedure.
Right.
The primary claim, and the true victory of the paper, is the massive input context compression. You are freeing up thousands of tokens in your context window for actual user data or retrieved documents, rather than burning that space on static instructions.
All while preserving or boosting the model's accuracy, which, to be fair, solves the exact problem we started with.
It really does.
But those are single-round QA tasks. You ask a question, you get an answer. The whole landscape of AI agents is moving rapidly toward long-horizon, multi-step environments. What happens when the AI is asked to navigate an environment where, say, step 3 depends entirely on what it observed in step 1?
Right. And here's where the researchers designed an agentic stress test. They utilized benchmarks like ALF World, which tests an agent's ability to navigate text-based environments.
Like exploring a virtual house to find a specific object.
Exactly. They also tested it on Office QA and spreadsheet tasks. They used successful trajectories generated by GPT 5.5 as the training data to try and teach these 32 virtual tokens how to execute complex multi-step procedures.
Here's where it gets really interesting, because this is where the theoretical miss in place completely falls apart. On the spreadsheet task, the hard text artifact, the long human-readable markdown file from a baseline they call SkillOpt, absolutely crushed the SoftSkill method.
It wasn't even close.
The hard text maintained an accuracy of 52.5. SoftSkill plummeted to 28.2. It fundamentally failed to compress long-horizon, multi-step procedural behavior.
It is a critical limitation, and we have to look at the underlying architecture to understand why it failed. It really comes down to the limitations of sparse trajectory imitation using next token prediction.
Okay, break that down for us.
In complex environments like ALF world, you have cascading action dependencies. You need robust state tracking. A 32-token prefix can easily absorb static preferences for a single math question. It can learn to format the output or cite a source.
Right, the simple stuff.
But absorbing a dynamic logic puzzle requires the model to hold on to a procedural structure over a long temporal horizon.
Because a static 32-token continuous vector sitting at the very beginning of the prompt can't act as a working memory buffer for branching logic.
Exactly.
It just doesn't have the capacity to dynamically update its state based on new observations 50 steps into a trajectory.
Precisely. The continuous prefix is a static preconditioning tool. It cannot dynamically reroute the model's attention based on evolving environmental feedback the way a comprehensive set of written conditional rules can.
That makes total sense.
The researchers point out that to bridge this gap, we likely need architectures that inherently preserve the procedural structure of the original text skill. Or we need to move beyond simple next token prediction to stronger, reward-based reinforcement learning updates for the prefix itself.
You can give someone the muscle memory to shoot a perfect free throw, but you can't give them a static 32-token muscle memory for how to manage a volatile stock portfolio over 6 months.
Great analogy. The environment just changes too much.
Which actually ties perfectly into this very strange dynamic the researchers uncovered about how the AI actually learns during the next token prediction training.
Oh, the training dynamics. They were highly counterintuitive.
Yeah, explain this, because it threw me off.
Normally, when you track the training loss in machine learning, a decreasing loss means the model is getting better at its objective. In this case, predicting the next token in the successful trajectory, you would expect that as training progresses and loss goes down, the model's performance on the actual task would go up.
But they found a complete disconnect.
A total disconnect.
Lowering the next token prediction training loss did not guarantee higher task success. In fact, they found that the best performing checkpoints, the versions of the soft prefix that actually solve the benchmark problems the best, were typically found incredibly early in the training process.
Right. For the single-round runs, they peaked at epoch 1 or 2 roughly 69% of the time.
Wow.
If they let the training continue, the loss kept dropping mathematically, but the actual task performance degraded.
Imagine practicing free throws, and the more you practice, the worse you perform in the actual game. Why does the model's actual task success degrade, even as its training loss improves?
This raises an important question, and the underlying mathematics of why this happens are fascinating. It indicates that the model is rapidly overfitting to surface-level formatting patterns.
Ah, formatting again?
Right. Remember, the next token prediction objective doesn't know what the actual task is.
Yeah.
It only knows it needs to predict the exact sequence of tokens in the training data. So in the later epochs, the 32 virtual tokens become highly optimized for imitating local action patterns, specific phrase lengths, or stylistic quirks of the training examples.
So it minimizes the loss mathematically, but it completely loses the generalized semantic logic required to succeed at the actual task.
Exactly. It's optimizing for the structure of the answer rather than the correctness of the answer.
So if the training data always features a 5-word answer, the prefix learns to force a 5-word output, even if the math requires a 6-word explanation.
It memorizes the shape of the test rather than learning the subject material. This architectural quirk is why the researchers had to implement a strict validation gate.
They couldn't just rely on the final train checkpoint.
No, they had to constantly test the intermediate checkpoints against a held-out validation set to evaluate true task success, and then export the earliest, highest-performing checkpoint. The validation selection is a fundamental requirement for making this compression method viable.
And there was another architectural detail they explored regarding what they call prefix geometry. They looked at the mathematical shape of these learned virtual tokens in the high-dimensional space of the model.
Right. They wanted to know if it mattered how you initially built the prefix before you started training the soft delta.
And they proved that the initialization point is critical. They found that prefixes initialized from the natural language text embeddings performed entirely differently and grouped differently mathematically than prefixes initialized from just random mean pool embeddings.
Which means the natural language starting point actually anchors the virtual tokens in a useful region of the model's latent space. It provides a task-dependent structural bias that random noise just can't provide.
It gives it a head start.
It does. But the probes also revealed significant geometric drift.
Geometric drift.
Yeah, as the soft delta is trained, the learned prefix doesn't just sit there acting as a slightly blurred mathematical copy of the original English text. It actively moves.
Oh, wow.
It shifts its geometry through the model's high-dimensional space based on the specific task constraints and where it's injected into the context window. It sheds its relationship to human syntax entirely and morphs into a highly optimized conditioning object tailored specifically for that exact model's architecture.
So it completely detaches from the English language and becomes pure mathematical instinct.
Pure instinct.
So what does this all mean? Looking at the entire landscape of this research, the massive context savings on QA tasks, the clear limitations in multi-step agentic environments, and the delicate balancing act required during training, where does SoftSkill actually fit into a production environment today?
We really have to contextualize it against full parameter-efficient fine-tuning methods like LoRa. SoftSkill is not designed to replace LoRa.
Okay, that's an important distinction.
Right. If you have the data set, the compute budget, and the serving infrastructure to manage custom model weights, doing a full weight update is still going to yield the maximum possible accuracy. The paper's own ablation studies show LoRa outperforming SoftSkill on Search QA when given access to 100% of the training data.
Because LoRa updates the actual reasoning pathways throughout the layers of the model rather than just preconditioning the input at layer 0.
Exactly. But SoftSkill's advantage is its highly practical deployment footprint. It is an exceptional tool for input-side adaptation on completely frozen models.
So you don't have to manage custom weights or specialized infrastructure for every single skill your agent needs.
No, you simply inject this lightweight 32-token vector into the prompt. It reclaims massive amounts of context budget for retrieval, augmented generation, or data processing, and it remains highly competitive in low data training regimes where you just don't have enough examples to properly train a LoRa.
And from an operational standpoint, you kind of get the best of both worlds regarding auditability. You don't have to throw away the markdown file.
Right. You can keep the human-readable text file in your database for your engineers to review, to debug, or to use for routing logic.
But at the exact moment of inference, when the AI actually needs to execute the task, you swap out the verbose English text for this hyper-efficient 32-token instinct.
It successfully decouples human readability from machine execution. You maintain the auditability of text while deploying the computational efficiency of a continuous latent vector. It really is a highly elegant architectural compromise for deploying scalable AI agents.
It really is. It's like keeping that 10-page coffee manual safely filed away in the HR cabinet just in case management ever needs to review the official company policy. But when your brilliant employee actually walks into the kitchen, they don't look at it. They just rely on pure, optimized muscle memory to get the job done instantly.
That's the perfect way to summarize it.
Which leaves me with a final thought for you to consider, something that goes a bit beyond the immediate benchmarks of this paper. We are currently watching researchers successfully compress complex human language instructions into 32 virtual mathematical tokens. These are tokens that only the machine's specific architecture truly understands, completely untethered from the constraints of human syntax and grammar.
Right.
If this method of behavioral compression continues to scale, and as we move toward ecosystems where multiple AI agents are interacting with one another to solve complex problems, what happens when they start bypassing human language entirely? Imagine a scenario where swarms of agents are sharing and trading these latent soft skills directly with one another, passing pure, continuous mathematical vectors back and forth at lightning speed.
It's wild to think about.
It would be an exchange of instinct completely unreadable to us, but perfectly geometrically optimized for them. We might be looking at the foundational architecture for a completely post-language AI ecosystem. Something to think about. Thank you for joining us on this deep dive. We'll catch you next time.